If you've spent any time at all looking at body imaging protocols, you know that feeling.
Oh, absolutely.
The sheer variety of MRI pulse sequences, all the acronyms, TSE, SEPI, KP-UNYA, it can be genuinely daunting.
Right, and that's true whether you're a trainee or even an experienced imager just trying to keep up.
Exactly. The complexity is just, it's real.
It is. The number of tools in the MRI toolbox is growing exponentially, but if you don't have a solid framework for why you're choosing a sequence, it quickly becomes protocol chaos.
And that is exactly why we're here today. This deep dive is really designed for you, the learner, to cut through all of that. We want you to understand the strategic framework behind it all.
So you can look at anybody, MRI protocol, liver, kidney, whatever, and instantly know the purpose and how to maximize that diagnostic value.
Okay, so let's start there. Let's build that framework.
Mm-hmm.
You say most protocols, despite all the options, can be boiled down to just 3 essential categories.
That's right. 3 core pillars that really define any solid body protocol.
So what are they?
First, you absolutely must have T1-weighted gradient echo sequences, or GRE.
Okay, but why T1 specifically? I mean, can't T2 tell us something about the tissue composition too?
T2 is fantastic, but for fluid and edema, T1 GRE is really the king of composition. It's vital because it lets us evaluate chemical shift.
Meaning you can spot microscopic fat.
Exactly, like in an adrenal adenoma. And just as important, it helps us evaluate magnetic susceptibility so we can map things like iron in the liver or even find air. It's your tissue signature.
Got it. Okay, so pillar 1 is key 1 for composition. What's the second?
The second pillar is fat-suppressed T2-weighted sequences.
Workhorses.
They are the workhorses. We use them to increase lesion conspicuity. Basically, you suppress the bright signal from fat, and suddenly any abnormality, an abscess, a tumor, anything with free water, it pops. It stands out like a beacon.
That makes perfect sense. So you're increasing the contrast between the problem and the normal background.
Yeah.
And the third pillar?
The third is your T1-weighted dynamic contrast enhanced sequences, DCE.
This is for after you inject gadolinium.
Precisely. This is the key for detection and characterization. We watch how tissue enhances over time. Wash in, wash out, arterial phase, venous phase. That dynamic information is what fundamentally dictates whether we call something benign or malignant. If you have those 3, you're set.
Okay, let's unpack this. Let's start with one of the biggest challenges in imaging the abdomen and pelvis, which is just movement.
Respiration and peristalsis.
Yeah, it degrades everything. So we need to talk about speed. How do we accelerate these acquisitions?
Well, the foundation for years now has been parallel imaging, or PI. It uses these sophisticated multi-channel surface coils to strategically undersample K-space.
So you're cutting out steps.
You're cutting out phase encoding steps, which means you're collecting less data so you can scan much faster.
What's the trade-off? There's always a trade-off.
There is. The benefit is huge speed. An acceleration factor of 2, for example, cuts your scan time in half. But the cost is a drop in the signal-to-noise ratio, SNR. The image gets faster, but it also gets a bit grainier.
And we hear about different types of PI all the time, Sense and Grappa. What's the practical difference for us?
This is a great clinical takeaway. So Sense performs its reconstruction and unwrapping in the image space after the data is acquired. It tends to be very fast and gives you good SNR.
Okay.
Grappa, on the other hand, unwraps the data within K-space before the final image is even made.
And how does that difference actually change what we see?
Grappa is just more robust. If you're imaging a region that's really inhomogeneous or you're expecting a lot of motion like in a difficult abdominal scan, Grappa often handles the artifacts better. So think Sense for pure speed, Grappa for robustness when things are messy.
And speaking of acceleration, that brings us to K-Purina, which is critical for those big 3D scans.
It is. K-Purina takes parallel imaging and just applies it brilliantly to 3D. See, in 3D, you have 2 phase encoding directions.
Right, in plane and through plane.
And K-Purina lets you accelerate in both directions at the same time. You could get a total acceleration of arcwheel 4, say, by doing 2 in one direction and 2 in the other. It's a huge time saver for those long 3D acquisitions.
So if parallel imaging was the evolution, then I feel like compressed sensing, or CS, is the revolution. This is where you see the vendor names, right?
Yeah.
Hypersense, compressed sense.
The name doesn't matter. The principle's the same, and it's really cool. Traditional MRI says we have to sample all of K-space.
Right.
CS says, no, you don't. It uses a semi-random undersampling of K-space, so we're deliberately taking only a tiny fraction of the data we thought we needed.
And then what? How do you get an image from that?
That's the magic. This highly undersampled data gets fed into a very sophisticated denoising algorithm. It's kind of like Taking a few random puzzle pieces and letting an AI figure out the rest of the picture with stunning accuracy, it just markedly reduces your acquisition time.
And another big one for speed is simultaneous multiple section, or SMS.
SMS is a huge win for clinic throughput. It uses special RF pulses to excite 2 or more sections at the exact same time. For body imaging, an acceleration factor of 2 is pretty typical.
And the impact is huge.
It's massive, especially for long sequences. We've seen it take MR enterography scans from nearly 6 minutes down to under 4 without any meaningful loss in SNR. That's a huge difference for patient comfort.
Okay, let's pivot from speed to our second pillar, fat suppression. You said it's crucial for making lesions pop, but not all methods are the same.
Not at all. And this is where choosing the right one becomes diagnostically critical.
Let's start with the inversion recovery family. So stir versus spare. Stir is known for being super robust, right?
It is. Short T1 inversion recovery, it's the gold standard for homogeneous fat suppression. Because it's based on T1 time, not frequency, it's great near metal or over large, messy areas.
Yeah.
But it has 2 major limitations.
Oh.
1, it has a lower SNR. And 2, and this is the big one for any learner, you cannot use STR after giving contrast.
That's the key diagnostic trap. Why is that?
Because gadolinium is a T1 shortening agent. So when gadolinium collects in an enhancing lesion, it shortens that tissue's T1. If that T1 value gets too close to the T1 of fat,
The STIR pulse just nulls it out. It thinks it's fat.
it thinks it's fat. You could completely obscure an enhancing tumor or an active endometrioma. It's a massive pitfall.
A perfect explanation of that contrast conundrum. So if you need T2 fat sat after contrast, you have to use the spectral method, spare.
Precisely. Spectral attenuation inversion recovery. It uses a fat-selective pulse that targets the specific frequency of fat, not its T1. That means it has a higher SNR than S-star, and crucially, you can use it after contrast without any fear of suppressing what you want to see.
And then there's the Dixon method, which has become incredibly popular.
Dixon is probably the most versatile and robust modern method. It's based on the chemical shift between fat and water. You get an in-phase and an opposed-phase image, and then from that, the scanner calculates a water-only, your fat-suppressed image, and a fat-only image, all with no extra time penalty.
And the robustness of Dixon's water-only images is key.
It's fantastic, especially in, say, obese patients, where the B0 field is really inhomogeneous or near areas of susceptibility. Plus, it's invaluable for characterization. You can look for microscopic fat with the opposed phase, or use the fat only to perfectly outline a myelolipoma. It's just incredibly powerful.
Okay, we've covered speed and conspicuity. Let's move to the final frontier. Going from just seeing things to actually measuring them. Let's talk quantitative and functional imaging. And we have to start with diffusion-weighted imaging, DWI.
Right. DWI is this powerful tool that measures the random Brownian motion of water molecules in really cellular things like tumors or abscesses. That water movement is restricted.
And that restriction shows up as high signal on the DWI images.
Exactly. But we have to constantly remind ourselves, and you, the listener, about the T2 shine-through trap.
Hyperintensity on DWI alone is not enough.
It is the most critical diagnostic trap in DWI. Any tissue that's just naturally bright on T2 can also look bright on DWI. That's why you must always, always look at the apparent diffusion coefficient, or ADC, map.
So what's the rule?
True restriction is bright on DWI and dark or high pointance on the corresponding ADC map. If it's bright on both, it's just T2 shine through. That distinction is fundamental.
And DWI gets notoriously messy near metal, like a hip replacement, especially at higher field strengths. What's the fix?
Standard DWI is usually single-shot EPI, and it's terrible near metal. That's where you need something like readout segmented EPI or RSEPI. It breaks the acquisition into smaller, less distorted chunks. It dramatically reduces that geometric distortion and artifact.
So you can actually see what's happening around the prosthesis.
Yes. The trade-off is a slightly longer scan time, but it's a huge clinical win.
Let's shift to the liver then. This is where quantitative metrics are really changing the game for chronic disease.
We are absolutely moving toward non-invasive biopsies. Using automated software on 3D multicode Dixon images, we can calculate 2 crucial metrics: the proton density fat fraction, or PDFF for fat, and the R2 value for iron. And these have been shown to correlate incredibly well with biopsy. Imagine telling a patient they have exactly 31% hepatic steatosis without a single needle.
That's precision medicine. And we could do something similar for fibrosis with elastography.
Right. Elastography measures tissue stiffness We use a little acoustic driver, like a paddle, on the patient that sends shear waves through the liver, and the MRI machine measures how fast they travel.
And a stiff fibrotic liver means faster waves.
Exactly. The quantitative values are just crystal clear. A normal liver is around 2.3 kPa, advanced fibrosis is maybe 4.8 kPa, and cirrhosis can be up at 13.0 kPa. It's an objective, non-invasive measure of their disease stage.
Okay, let's pull all these tools together. How do radiologists customize a protocol to answer a very specific clinical question? Let's take MRCP for the biliary tract.
For MRCP, the big decision is often 2D versus 3D. 2D MRCP is fast, just a few seconds for a thick slab, but it's prone to motion and you can miss small stones.
Whereas 3D gives you that beautiful high-resolution volumetric data.
Exactly. 3D gives you thin 1mm sections. You can do MIPs, reformat it any way you want, but it used to require respiratory navigation that took several minutes.
So what's the modern solution?
This is where you combine techniques. You use a breath hold compressed sensing 3D MRCP, and suddenly that acquisition time can drop to just 10 or 15 seconds. You get the resolution of 3D with the speed of 2D.
We can also customize based on the contrast agent we use, specifically gadoxetate, which you might know as Eovist or Primovist.
Gadoxetate completely changes the game because healthy hepatocytes actually take it up. This allows us to do hepatobiliary phase or HBP imaging about 20 minutes after injection.
And that 20-minute gap is a huge opportunity for protocol optimization.
A massive opportunity. Think about a rectal cancer staging protocol. You need to stage the tumor locally, but also check the liver for mets. So you inject the gadoxetate, get your dynamic vascular fluids, and then you use that mandatory 20-minute waiting period to acquire all your other sequences. The T2s, the high-res pelvic images, the DWI. It makes for an incredibly efficient protocol with zero wasted time.
Speaking of cancer staging, precision in the pelvis is just. It's absolutely non-negotiable.
It is the difference between a patient going straight to surgery or getting life-altering preoperative treatment. Your thin section, high-resolution, small field of view T2 sequences, they are the absolute mainstay for T-staging.
Can you give us an example of where that precision really mattered?
I remember a case, a rectal tumor that looked pretty well contained on the standard large field of view images.
Okay.
But when we put on the specialized high-resolution small FOV sequence, it revealed a tiny 2mm focus of extramural venous extension, just a minuscule detail.
Completely invisible otherwise. And that changes everything for the patient.
It changes everything. That one tiny finding upstaged the cancer. It changed the management from immediate surgery to neoadjuvant chemoradiation. That 2mm finding, enabled by one specific sequence, led to the absolute best outcome for that patient. That's why we obsess over this.
And just quickly, for vascular issues, how do we capture dynamic flow?
For that, you need time-resolved MRA, things like TWIST or TRIGUS. These use really aggressive case-based sampling to get frame rates of 1 to 2 frames per second. It lets you map out the arterial inflow and venous outflow of something complex like an AVM, which is essential for planning.
What a fantastic journey. We started with what feels like this daunting, endless list of acronyms, and we've pulled it all together into a strategic framework. It's about speed, composition, and function.
It is.
And the key takeaway for you, I think, is that understanding the purpose, the why behind what you're doing, is so much more valuable than just memorizing every acronym.
That is exactly right. If parallel imaging lets us scan faster and high-res sequences let us see tumors that are only 2mm deep, we've really established a new foundation. So the provocative thought I'll leave you with is this. Given how precise and reliable these new quantitative metrics are, elastography for fibrosis, PDFF for fat, what's their future role in screening in managing chronic disease, could they one day reduce or maybe even replace the need for traditional invasive biopsies altogether?
The information is already there to be measured.
The next step is just applying it,
Yeah.
universally.